next presentation is about the symbolic reasoning in telecom-oriented large language models. Our presenter is Ali Mokh, and the research concept AI at Ericsson. This talk explores the integration of symbolic reasoning into telecom-oriented large language models, enhancing their capacity for logical interference, rule-based processing, and deterministic problem solving. Ali?
Thank you very much. How I can switch between slides for the switching? Yeah, thank you. Hello, everyone. Thank you. So I'll introduce myself. My name is Ali Mokh. I'm working as a researcher in AI, generative AI mainly, and also part of my work, MLOps in Ericsson. So Ericsson is one of the leading technology makers for telecom infrastructure. And I'm part of a big team inside Ericsson called System Comprehension Lab that we are developing and using GenAI tools for Ericsson, either for internal use or for customers. So in this presentation, I will have brief introduction just to align that we are all talking the same language, make sure. Maybe it will be repetitive for you after all these presentation, great presentation about GenAI and agents. And I will move to what is the AI native wireless systems, how we define it, where we are heading towards, what are the limitations of the current LLM, and why we are thinking about symbolic reasoning to be combined with the LLM to solve telecom problems. So basically, quickly, you have seen this picture, I think, a lot of time. What I need to mention here quickly is that GenAI, while it has been conceptually understood that it's part of deep learning or neural network, but we have a lot of GenAI, generative AI models that are not deep learning or not neural network based. But since the majority are a neural network, this will lead us to understand how they are treating information in finding patterns and matching these patterns. And also the LLM, while they are taking over most of the use case, mainly because of the transformer architecture, they are a subpart of these GenAI models. So how we see the faces of GenAI applications so that we can position ourselves as Ericsson in this field. We have the first part, which is the pre-training part, where we have, like, we need to train model from scratch to understand language and semantics from base. It's like taking a baby and teach him how to speak languages. So this is the most complex part to create pre-trained model. This is what Google, Meta, Anthropic, Mistral, and OpenAI, they are working on. Ericsson is not yet interested in building these in pre-training model. It's more efficient to take pre-trained model and adapt it to our use cases. From here, we are working on the two consecutive steps. Adapt to some task. We have some use cases, like, for example, today we have a lot of models that are built to do question answering, code generation. So they are instructed in this way to be adapted. And this is very important when we are building multi-agent framework on top of, like, LLM-centric architecture. We need to pick the right model for the right use case. And finally, we need to adapt it to the domain. And so this is, like, the most used part by most of people. It does not need, like, ground base in GenAI. Today, we can build it with, like, open source solution with a few line of codes, or going to AWS console with a few clicks, we can create an agent. How we do adaptation to domain? We have the 3 customization technique. We have the prompt engineering, the RAG, and the fine-tuning. Here we can see the complexity of each one. Prompt engineering, everyone is doing it by using ChatGPT every day. And like, we can instruct him how to do things. And then we have the RAG, where we can augment our LLM or our model with our internal information. Well, there is the simple layer of building a RAG, and there is the complex layer of building the RAG. We know that today with open source solution, we can create a simple RAG, but actually garbage in, garbage out. If we don't have a good data representation or decomposing of the documents, we will not have some good outputs. And the difficulty starts when we think about the fact that our question is not related to an information that is in certain part of this document, but it's a relation of multiple documents and multiple information in different areas. So here where the first complexity came, and the second complexity is that we have some multimodal documents where the information is embedded not only in the text, but also in figures and in the position of the figures inside this text. So let's say we have PowerPoint presentation. This PowerPoint, it has some text. Sometimes the alignment of this text can present a flow diagram or something like that. And so this is what we call the meta information inside the document. It needs to be extracted also and understood by the LLM to be able to answer our question. And finally, the fine-tuning. This is very specific today to be used because we have already a lot of LLM in open source that have been fine-tuned for specific use cases. For example, code generation. We might have some extra thin layer using LoRa to adapt this model to our code repository or our small documentation if we're talking about standards. Finally, I need just to quick talk about multimodal models. So basically, these new models that we are using that can handle multiple modality, and this is what interests us. They are built in a way that the transformer architecture can, with encoders, understand information from multiple modality in the same data layers. So we have the same latent space that can look to an image of Apple and the word of Apple. And similarly here, we need to adapt this to the telecom infrastructure. So in AI native wireless system, just to position ourselves how we need to leverage these technologies, we are thinking about building telecom infrastructure that can automatically use AI to enhance its capability while by increasing efficiency, reducing intervention time, etc. So they have AI deeply integrated, and we are moving towards this fact in multiple steps or multiple layers of intelligence. The first layer starts by taking each component. So we have the OSI layer of the telecom that starts with physical layer and MAC layer and network layer all above. So for each layer, we have multiple components in telecom infrastructure. And in these components, we started with small components that are using AI. For example, for downlink layer adaptation, we started to use AI in some mini component to adapt the configuration for the user experience. The next level of intelligence is that we have single AI that can manage the whole package of channel estimation of the downlink layer adaptation, etc. Each one in different OSI layer. And finally, to go toward an AI native layer. So we have single AI. All the physical layer is handled by one AI, okay, optionally. Now we start to talk about also another layer of intelligence where we have an intelligence that can control all these layers across multiple layers together at the same time. So, and also in what are the characteristics of AI wireless system, AI native wireless system? First, they are self-optimized, so they can automatically adjust the parameters dynamically for the use case. We have increase in, for example, let's say there is a manifestation or there is any concert today happening, it will be automatically adapt the resources to handle all these modification in this area. Or today, like let's say we have strike, we have less people going in this place. I can turn on or off some frequencies to reduce energy efficiency. We have real-time decision making. Also, The AI will enable the system to make quick decisions also that are data-driven. And we have predictive capability. It can forecast also if we will have more users connected to this. For example, it adapted in a way that at this period of time, we see that we will have more users connected to these base stations. So let's increase our power, let's use more frequencies, etc. But what is important here to see in this picture is that telecom infrastructure has been evaluated in the same way, like let's say in parallel with the evolution of the software development infrastructure. They both serve themselves. In 4G, we focused on having mobile broadband where we connect our telephone that became a mobile computer. Okay, we have all the computer use cases, and it is IP native. We can access internet with very good connection. In 5G, we changed the strategy that we are service-oriented. So today, we need to have multiple networks. Each network is adapted to some use case. For example, we have ultra low latency, ultra reliable and low latency communication, let's say vehicle to vehicle, or communication that needs quick response. Sometimes we have use cases where we have communication for let's say 4K communication, or IoT where we have a large number of sensors. So each one, it needs an optimization that is different from the other. So that's how we started to talk about 5G differentiated service. This happened because the fact that our software development infrastructure also changed. We moved from native, from electronic devices or purpose-built device into virtualization and cloud native toward multi-cloud. And today, since the software development infrastructure is moving toward AI native, the telecom infrastructure is taking benefit of that to move toward AI native. So the forecasting in 6G infrastructure will be also AI native, where we have AI embedded for wireless network to automatically manage and adapt for the use case. So how we see the architecture? So we have in the middle a reasoning engine that is AI native. Let's say it can be an LLM or multiple LLM, multiple agents, etc., with connectors. We have the first part, which is the information, multimodal information. But for wireless network, we have much more modalities to talk about. We have logs, we have videos, we have wireless sensing, information, localization, etc., etc. And also we have documentation for standardization. For each one of these modalities, we need different encoders and different translators, pipelines to be built, purpose-built pipelines. So eventually, we might have all these modalities combined, coming to the same latent space, to the same language that our reasoning engine can understand. After the reasoning engine is connected to some tools, these tools, it can be some SDKs, APIs to fetch some information, to write some information, create YAML file for new configuration, etc. And that's how we can go towards intent-driven run, where we can request to enhance our infrastructure linguistically, and it will automatically adapt our telecom infrastructure to answer this request. So this is just a recapping of what I described before. I will skip it. So with this architecture, what we have some challenges and limitations. First, hallucination is something that we cannot bypass in LLM. It's happening because LLM, they are built as a statistical model and trained on some data. Bayesian probabilistic model. So the hallucination is something that we cannot avoid. So we will have unreliable reasoning, especially for telecom use cases. Second, the chain of thought, which is the best framework today used for reasoning in LLM, actually it's not logic. It's not making logic. It's just adapting the reasoning, or like adapting the probability distribution of the LLM to follow some kind of logical steps. So it still makes some arithmetic and consistency errors. Third one, LLM are black box. So here I came back to the fact that most of LLM are built on top of transformer, which is neural network architecture. Neural networks, because of the gradient descent way of learning, it's still black box. So having the description or why this answer is given is still something difficult. The explainability of the LLM is still an issue. And this is crucial in telecom, because if we need to change the infrastructure, or we say there is an alert of fraud, we need to understand why before taking any action. And finally, it's data-trained models. Okay, we see that it's very efficient when talking with language-based use case, write an email, write an essay, etc., because it's learning on gigantic amount of data. But when we are talking about telecom infrastructure, whenever we are building a solution that is data-driven, there is always black swans, lot of black swans. Okay, so data, they are not consistent all the time, so it will struggle with the out-of-distribution network events. We still always will have some new events to deal with. So to solve this, we need some kind of reasoning and taking some general intelligence instead of just following the trends. So here, we are combining the limitation of the telecom and the software development use case. Both of them, each one has its own umbrella of limitation, sometimes shared, sometimes separated, but we need to think in the same way. So for the telecom-centric, our problems that we have a lot of modalities, as I described, radio sensing, well, images and sound and text, they are solved today because most of people are interested in this modality, but we have a lot of other modalities in the telecom. Data is not stationary, so the probability distribution, I would say, of the data that's used for pre-training the model is not covering what we have in the telecom infrastructure, right? So let's say I used all the data in the internet. It does not include all the probability distribution of what's happening in the telecom infrastructure. This is very dedicated. And we have high uncertainty in diverse and dynamic environments. So when we have some environment where changes occur quickly, we have a lot of uncertainty of what this LLM will be giving, because it is probability oriented. So how we think we can address this for the telecom-centric problem? First, we can address this with digital twins. In digital twins, we can run a lot of scenarios to think that mimic the real use case. But the problem here that the problem arises about the affordability, because running a lot of scenarios to train the LLM, it will cost a lot. And some architecture might boost AI efficiency. For example, open architecture or cloud native to have a lot of data sources. Let's say all operators and all technology makers will join some open source consortium to share their data. So similar to how much we have data in the internet for natural language, we need something similar in telecom, okay? And enable separating computing resource for the same task over the network stack. So basically, this is today, one of the example is GPU as a service. For example, I need some GPUs sometimes to train or optimize my telecom infrastructure, but I don't need it all the time. So to speak about affordability, I can have GPUs in my G-Node-B, in my telecom infrastructure, that I can put it on rental for other use cases, okay? So people can use it, let's say, similar to AWS. I need to run my AI model. Once this GPU is not used by the telecom provider, it can be used by someone else. So we still have some questions, how we can architect the network for optimal AI performance or AI native. On the other hand, there is still some challenges that are AI-centric or, let's say, software development centric. So chatbots are very cool, but they still lack for reasoning and common sense. So this is today what's known about how to move toward general intelligence, how we can reach the general intelligence in AI and chatbot. They are training-centric and data-dependent. So that's why you see that we train a model on gigantic amount of data, but it's still lacking to understand some information, let's say specific language that few people are talking, or like a specific domain, etc. So every time we have an LLM, it's very specific to the data that it has been trained on, okay? And this is referring to the neural network architecture. Also, we have the model collapse and the hallucination. So we are implementing some prompt engineering way, or sometimes fine-tuning way to reduce hallucination, but we cannot avoid the hallucination at all. What are the architecture that are proven to work best for telecom? Actually, till now, this question is not solved. Apparently, it's more like combination of architecture. So that's why multi-agentic framework is more adaptable for telecom, because telecom, it's not a language. It's more complex than a language. It's a domain that includes a lot of languages in multiple layers that are speaking between each other. So here we can take what Andrew Karpathy also used to use this example. We need to move from system one thinking to system two, as described in Daniel Kahneman's book. So today's AI and LLM, they are in system one, they are intuitive, they are more adapted to what they have seen. It's a quick answer, but we need to move into system two that is deliberate, slow, but it is logical. It follows a structured way of thinking. So that's why we are interested in the hybrid AI, so neural symbolic AI. So symbolic AI, as described before, it's a rule-based AI. So it happened to be used a long time ago, and now it's back. It used to work with expert system. So it will use explicit logic rules and knowledge bases. So basically, we have some knowledge base and we have some rules that are rule-based driven. We need to use. This is combined with the neural network. So neural network is the base architecture of the transformer or the LLM. They are very good in extracting pattern and pattern recognition, and we use them, like the main reason why we use a neural network architecture against other architecture, that it is scalable and it can be trained in parallel. So that's why this is the main part why we are using the transformer, that we can train it in parallel and we can scale it up. It means more transformer, better LLM. That's what we have today. So to combine both of them, to have neural symbolic system where we have neural network, but again, trained or forced to follow some rule-based logic, we are connecting these two together with tools like, first we can start with something similar to prompt engineering, what's called symbolic chain of thought. So we will have a chain we are pushing the LLM, to follow some chain of event or thought with symbols. So let's say P imply Q, so non-Q imply non-P. That's how you should think. So we are teaching the LLM to follow logical way of thinking, or, which is most used, is program-aid reasoning. So sometimes we can have a rule-based AI that is working as aside, and it's very efficient. So we will use the PAL framework, where we let the LLM use this tool to run the AI or to answer. And finally, integration of external solvers, similar to the program-aid reasoning. We can take this solver as another agent or another tool that we are calling. And so the interest here is to move in our way of reasoning from data-driven. So data-driven is, let's say, looking to the data and answer to the data. So that's how the wireless network are tied to the data. For example, we used to have tables of what is the best QoS tag for this use case. Okay, that's how the infrastructure is built in the 4G. We need to go afterward into information-driven data. So this is the basic AI, where we have some AI that is learning from what's happening. So they are application aware and they are quasi autonomous. So for this application, we need to use this way of working in the wireless network. And afterward into knowledge driven. So this is how we see the generalized intelligence of the wireless network. We have some network that can learn from the experience using reinforcement learning. You are using more advanced AI capability to do some transfer learning, to do some generalized information across multiple layers. And finally, the higher reasoning level, which is like human-like reasoning, is reasoning-driven, where our wireless network, they are AI native and they can run some versatile logic. So they can connect dots between each other and perform some logic association. For example, using semantic communication. With semantic, the transmitter can send only some few tokens that the receiver will be able to decode and understand. And that's how we can go beyond Shannon limitation. I think I crossed the time. Yeah.
A little bit, we are running out of time.
Yeah.
But of course, if you have one more slide, we can
Yeah.
go.
I will jump just quickly to the use case because this is what people maybe they are interested in.
Definitely.
So today, first application of neural symbolic reasoning we are using is for network optimization. So for network control, the LLM agent can perform long-term planning. So we give him the intent, and it will perform a planning about how to optimize this specific network. Second is the cross-layer reasoning, because what we have today, each layer is reasoned separately from the other, the physical layer, the MAC layer, and the network layer. But with this tool, we can reason across layers. So if I need to increase efficiency, the agent will be able to play with parameters across all these layers. And finally, we have dynamic optimization, where it can, on the fly, optimize the infrastructure. And the second thing is anomaly detection and security. We are analyzing logs, and where we see in this field that only LLM or only pattern recognition is not enough. We need some rule-based effort also to be built, to be connected to the LLM, to detect the attack. We have improved threat detection also. So because of the fact that rule-based can extract some meta information, and the LLM, it can reason across this information, it can have a better threat detection. And finally, we have adapt security policy, where we can request to the LLM linguistically how to change the policy, and it will implement these new rules to our product. Yeah. Thank you very much, and sorry for taking too much time.
No, it's totally fine. The topic is great, actually. Yeah, the applause for us.